Okay, so I'd like to show you some examples of how to compute work, and I've got four of them here, partitioned off into these four quadrants that you see. So starting with the one that's on the top left, consider a situation where you have a mass m on a frictionless surface, and it's being pushed to the right with a force F through a displacement delta x. And so in other words, the mass is moving from here to here in the same direction as the applied force. First of all, the work done by the force is the force times the displacement times the cosine of the angle between the force and the displacement. So the angle between this and this is 0 degrees. And so that would mean F delta x times cosine of 0. Cosine of 0 is 1. The work done is simply F times the magnitude of the displacement, delta x. Consider next the work done by the normal force. That's the force of the surface pushing upward on M. And in a similar fashion, the work done by N is N times delta x times the cosine of the angle between N and the displacement. That angle is 90 degrees. The cosine of 90 is 0, and therefore there are 0 joules. In other words, no work is done by the normal force. Similarly, the work done by the downward mg is also 0 because it too has an angle of 90 degrees with respect to the displacement. Next example, top right, is what happens if we first of all add friction. So you can see there's a frictional force pointing off to the left here. And we apply a force to the right, but we angle it with respect to the horizontal, so that it's angled, let's say, 30 degrees with respect to the horizontal, and that the mass m undergoes a displacement of delta x in the direction shown. And so let's find the work done by the force F. This force applied at an angle with the horizontal. And so as usual, it's the magnitude of the force times the magnitude of the displacement times the cosine of the angle in between the two. Cosine of the angle in between the two is 30 degrees, this angle right here. And so it's F times the cosine of x times the cosine of 30. But since F times the cosine of 30 is F sub x, that's also equal to F sub x times delta x. And just remember that this notation means the x component of f. Similarly, we can find the work done by the frictional force in this direction. And so when we apply the formula, we take the magnitude of the frictional force times the magnitude of the displacement times the cosine of the angle between the frictional force and the displacement, which is 180. They are anti-parallel. In other words, cosine of 180 is minus 1, and therefore the work done by friction is minus F sub f times delta x. And so this would be negative work. This would be positive work. Let's further consider the situation, example of a ball thrown up with an upward displacement of delta y straight up in the air. And so the ball is going from here to here, upward displacement of delta y. And let's think about what work the force of gravity, which is downward pointing, does on this mass. Using the definition of work, it's going to be the magnitude of the force of gravity on the mass times the magnitude of the displacement times the cosine of the angle in between the two. Well, as you can see from here, the angle between delta y and F of gravity is 180, and that's negative, and therefore the work done by gravity is minus m times g times delta y. It's negative. Fourthly, consider projectile motion, where a projectile is thrown from the top of a cliff, say, and so it will go in a parabolic trajectory. It gets to the apex, let's say, and then it goes down to below where it was. And let's consider the work done when the mass goes from here to the apex, from the starting position to the apex. And secondly, we'll consider the work done when it goes from the starting position to this ending position. So look at this one first, the displacement to the apex. So we'd like to find what the work done by the force of gravity is for this displacement, and I'm calling it D in the picture here. And so that's going to be the force of gravity times the magnitude of the displacement times the cosine of 90, because what I'm doing is I'm breaking the displacement up into an x component and a y component. And so d times the sine, the cosine of 90, the x component times the cosine of 90, which is the angle between f grav and this, is 0, so that drops out, plus f grav times the y component, which would be this component right here. You can see it going up, times the cosine of the angle between this, the upward y component of this, and f grav, which is 180 degrees. And so the first term, as we've said, is 0, because cosine of 90 is 0. This is minus 1, and so the work done by gravity in going this displacement d is minus mg, that's f grav, mg is f grav, times the y component, and the minus comes from the cosine of 180 being minus 1. Okay, so the only thing that counts, in other words, is for this displacement is the vertical part of it. For the z example, where we want to compute the work done by gravity and going from here to here, similarly we break the z into an x component of z and a y component of z. And again, there's no work done by gravity on this z component of the displacement. All the work is done here. For the same reason as above, because the cosine of 90 is 0. And so the second term is the only one that stays in. The f of gravity, magnitude, the y component of the z times the cosine of 0. Cosine of 0 is 1. And so that's just going to be mg z sub y. This right here, in other words. This is positive work done by gravity. This is negative work done by gravity.